Hi, I'm Jacob. I'm going to give you a quick overview on how we're using op amps in a very simple way to be able to record small signals from the brain. So particularly in a neuroscience application, we're often dealing with signals that are not only small in terms of voltage, but they cannot source a lot of current. So we would say that they have a very high output impedance. So these are terms that you've likely already talked about earlier. So just as a very quick recap, here's an equivalent model of what a tetrode recording a neural signal next to a neuron might look like. And we've abstracted here the configuration of the tetrode into an equivalent circuit that has a resistive and a capacitive coupling. The details of that don't matter so much. The gist of it is that the tetrode cannot provide an arbitrary amount of current because it's just a very small capacitor, for instance, coupling it to the voltage emitted by the neuron. The fact that the neuron itself also might not be able to provide an arbitrary amount of current, of course, is also true. So in any way, we then have the electrode itself that provides some type of resistance, and then we have a long wire. The wire also acts as a capacitor, as you talked about. So there's a couple things happening here that affect our ability to just translate the voltage that comes out of our electrode or is present at the tip of the electrode to our measurement. And even though we're talking about tetrodes here, where our current is a capacitively coupled current, the same exact reasoning in electrical terms applies to ionically coupled electrodes where there's an exchange of ions, or to electrodes like an EEG. So let's look at this in a circuit simulator and understand a little bit what the problems are that are arising from this. Here's a circuit simulator set up with a fake neural data source. So in this case, it's just 60 hertz, which is a bit of an odd choice, but let's just assume that's what we want to record. Then we have an equivalent resistance for our electrode here for 300K. It doesn't really matter. Then a wire going up to our computer. And here I'm modeling the long wire that goes to the computer with a 1 ohm resistance and a 1K leakage. And then the other thing that this circuit does, apart from providing us with some model of a cable that needs to be driven, is we're also modeling the fact that maybe the computer or amplifier or digitizer in the end itself also needs a little bit of current to run. So let's just see what happens. So the output from here should be 2 volts. So let's see what comes out the other end. So let's run this. And we see that we have basically 0 volt arriving at the computer. And the reason is that the output impedance of our system, determined by the 300K resistor here, is relatively high. But the input impedance of our system, in this case, even the cable itself, is relatively low, which you can see there's a 1 ohm resistor here and a 1K resistor making a voltage divider. And in the simulator, it's very nice. You can see what the current is doing. So first of all, you can see that there's a decent amount of current flow down here to ground. Because the amount of current flow, we have a large voltage drop across this resistor here. So that's just straight up Ohm's law. And you can see on the left side here, we have 2 volt. But as soon as we step on the right side of this resistor, which is the tip of our electrode, there's basically nothing left. So this is just with resistors. And we talked about capacitive coupling and capacitive losses earlier on. So let's just rebuild this circuit. And I'm just going to switch out these resistors here with capacitors. So now you can see that basically the same thing is happening. The reason for that is that depending on the frequency of the time varying current, whether we put resistors or capacitors in terms of impedance, you can very broadly think about as being almost the same. The basic problem seems to be that we're drawing current from our source, and drawing current is not good because it distorts the signal. In this case, it distorts it to 0. And as we've talked about before, a op-amp has this nice ability to not allow any current to flow into its inputs. So let's just remove this piece of wire, and I've already set up the negative feedback here, and instead put a unity gain, so no amplification, right? Non-inverting op-amp. So now we still have the voltage on this side and the voltage on this side of the op-amp exactly the same. But what we have changed is that there's no more current flowing in. And that means that we're not distorting the voltage at the input. And so if we reset this, you can see that now basically the input and output is exactly the same because this resistor here, this capacitor, does not distort the measurement because there's no current flowing. The same exact reasoning applies when we go back to the resistive case. So now we have our signal back. And this is entirely due to the fact that we're not drawing any current from our electrode. We're just looking at the voltage without drawing current. It's obviously not 100% true in the real world. This is a simulation, but we're drawing an extremely tiny amount of current in the real world. So to recap, drawing current from our electrodes is an extremely bad idea because it distorts our measurement. In real world terms, it distorts our measurement even with a couple meters of wire to get from a mouse to a computer or something. It distorts it to zero. And the solution to that is to just not draw any current from the electrode. And we're doing this by putting a non-inverting op-amp here, which, as you talked about, doesn't take any current into its input, but yet has the ability to provide the same voltage. So one way to talk about this in the language of impedance is that we have a high output impedance source, which is our tetrode in this case, and we have coupled that to a very high input impedance input on the head stage now, on the buffer amplifier. And on the other side, we can say that the amplifier has a very low output impedance, which means it'll provide however much current is required for keeping the voltage at the output the same as the voltage at the input. This means that it can drive this cable, even though this cable is a pretty hungry consumer of current, it can drive that cable to maintain that voltage up here. And there's still some voltage drop here, of course, because there's a voltage divider that the amplifier can't do anything about. But the voltage coming out of the op-amp and the voltage at the input terminal of the op-amp are the same, and it's going to provide as much current as is required for that. So I think that concludes this video.